Hi, so in this video, we are going to talk about a new design pattern called as the Singleton design pattern. Now again, as I talked about in the previous two videos, every design pattern is meant to solve a very particular use case. So what does this design pattern helps us in solving? So well, this design pattern is meant for managing the global variables. Now I know that you would have heard it tons of times that we should not use global variables because again they bring in a lot of issues, right? So global variables are very unreliable because they can be modified by anyone, right? Because they have a global scope, so they become very prone to errors, right? So that's one very big reason why we should not go for global variables. But there are situations where we have to have a single variable, a single global variable, right? And we want to make use of a single global variable, but we want to make sure also that that single global variable is not getting affected or is not getting manipulated or it's not getting instantiated multiple times, right? So depending on the use case, that global variable might be an object, for example an object to a database connection, which might be holding a connection to a database, or it might be an Kafka object, which might be a connection to a Kafka, or it could be anything else, right? So we don't want those global variables to be reinitialized again and again, or I should put this way, that we don't want that global variables to be initialized more than once. Now how do I make sure that, how do I prevent this to happen, right? Now since they're in the global space of the program, so anyone can access it, right? So we have to have a mechanism in such a way that these global variables are only initialized once, right? And for that itself we have a single design pattern, right? It's very simple. So if anybody asks you what is the role of a single design pattern, it's always to maintain, or it is always to systematically maintain the global variable state, I would say that way, right? Okay, now let's try to understand this thing. So if I talk about the instantiation of a global object or a global variable, and in order to prevent it from race conditions now, because global variable itself brings in a lot of issues. So I talked about one issue earlier, saying that since it's into the global space, it becomes very volatile with respect to its values, right? Because anybody can change it, right? So you're not sure what value a global variable will have at runtime. You cannot guarantee it. The second issue comes when you're designing a multi-threaded application, right? So when you're designing a multi-threaded application, the global variables or the global data become a contention point, right? They become the critical section, or they become the point of race conditions, right? So if two threads, let's say, are trying to access the same global variable or same variable itself, then it becomes a data race issue, right? So we want to prevent both of these issues, right? We want to prevent it from data race, and we also want to prevent it from unexpected changes in the value. So how do I do this? So one very short way is to have a mutex around that global variable, right? And that's how we do it. So in any concurrent programming, we make sure that we wrap up the global variable or the common variables with the mutex itself, right? And that's how we do it in general, right? So singleton design pattern also makes use of this mutex and locks, right? But the way we do it is pretty different here. It's not just about using a mutex or a lock, but it's also about how do we write these things in such a way that they become very efficient, right? So we'll go step by step and we'll see what all we have to do in order to write a singleton design pattern, right? Now, so I've already created a lock here, and this is going to be a mutex, right? So mutex only allows initialization only once, at least in Golang. We don't have a recursive mutex just like we have in C++. So a lock can be only locked once. That's one thing we have to understand. And let's say I have a single, I'm calling that as a single, and this is a class. So if you're coming from a language background, C++ or Java, we have classes as structs in Golang. Okay, so we have this single. So I can call this as anything, but I'm calling it as single for now. So this is a global object, a global class. I would call it as a global object or a entity. I would call it as entity for now. Let me just remove this object, not to confuse everybody. So I'll just call it as a global entity right now. Okay, so this is something which I want to update or instantiate, and I want to make sure that there is only one object for this global class or the single class, right? So how do I do this? So let's write one of the very crude way of doing this. is to basically use a mutex and just lock this object once and then work around it. So let's see the first way how we can do this thing. Okay, so if you see here, what I've done is I've introduced a new variable which is going to be my global variable, right? And now this global variable will hold the instance for this single class, right? So I only want to have only one single object for this single class into this single instance, right? Now I'm just taking this very weird name of single instance and single class, but you can get the idea that what I mean here is that this single instance will be holding an object which will be universally global to the entire program. Okay, so I've written the first way of doing it. So, and I've named it as flawed because there is some flaw with this approach, right? So let me call this as an approach 1, right? Now what is the flaw? Let's try to understand this. So if I just go through the code, what I'm doing here is I'm locking the mutex and then I'm using a defer to unlock it. Defer is just another way of unlocking any resources, because defer basically guarantees that even if there is a panic or even if there is a runtime issue in the code, this statement will always be guaranteed to be called, because unlocking the resources is very much important, right? Because we don't want that for some reason our code panics or breaks into some issue and we just lock the mutex, right? So it's good practice to always use a defer keyword for unlocking the resources or releasing the resources, right? Now here comes the meat of the code. Now what I'm doing is I'm basically checking whether the instance is single nil or not, whether it's empty or not. So obviously initially the single instance variable would be nil, therefore I'm creating a instance, right? So here I'm creating the instance and I'm assigning it to the variable, and then I'm also returning the same thing, or else I'll just say that it is already initialized. Now what is the problem with this? First let's see whether we are able to execute it or not. So I'll say get instance flawed, let me call this. Now if you look at here, I'm basically using the go prefix here. Now go prefix is essentially, that's how you basically create multiple threads. Just to be very precise, go doesn't has threads, it has something called as go routines, which is again an abstraction over the threads itself. But for a very simple understanding, you can say that these are just threads. So I'm essentially launching 30 threads, so it's a multi-threaded application, and then I'm waiting for all the threads to finish, right? So again, this is just a workaround to wait for the threads to finish. So here I'll be launching 30 threads and I'll see that whether I'm able to lock these, whether I'm able to instantiate more than one instance for this single class or not. So let me just go to the code, say run. So if you see here, it says the single instance already created. So if you see here, only for the first time, it says that, okay, single instance is being created, and for the subsequent threads, it all says that the instance is already initialized, right? So what's wrong with this code? Now at surface level, this looks very cool, right? This is all absolutely correct, but it is not good from a performance perspective. Why? Because what we're doing here is essentially we're locking the entire function in the beginning itself, right? So this function is essentially being locked in the very beginning and is being released at the very end, right? So from a very performance perspective, so if you have multiple threads running, this becomes a bottleneck, right? It's not a good design in itself, right? When we talk about performance. So is there any better way? Yes, there is. So let's talk about the second approach where we are going to optimize this for a better performance. So we have a second approach where we are going to optimize the same code for a better performance. All right. So if you look at this piece of code, this is the second approach. So what I've done here is, if you look at this from line 35 to line number 44, this entire piece of code is same as the previous one. Okay. What I've only done here is I've introduced a condition, a if condition beforehand. Okay, which basically checks whether the single instance is nil or not. Okay, and if it's not nil, then you simply return the instantiated variable instance itself. So you don't go with the locking and all, and you just return from line number 33, right? Now by introducing this extra check in the beginning itself, what you're making sure is that you are not locking unnecessarily. If you look at this previous code, for the first thread which acquires the lock, gets inside this and it basically instantiates the object, and then onwards, whichever threads come into, they are unnecessarily locking the code and they're then making check whether this instance is initialized or not, right? So I can say that for the very first time, this piece of code is executed and then we are basically instantiating the object. But after the first thread, from the second thread, third thread, fourth thread, and so on till end, whichever threads come into this function, they are all acquiring this lock, and then they are making a check. So acquiring a lock and then releasing it is itself is an expensive affair, right? Which we don't want to do because this hits the performance. So instead of acquiring this, because it's an expensive operation, let's also add another logic above this locking and unlocking mechanism, and that is what we have done here also. So what we have done is we have added an extra check here that if it is initialized, there is no need to even acquire the lock, just return back, right? And if it's not nil, that means, and if it's nil, that means that we have to basically initialize now. So that's the reason I go inside, I acquire the locks, and then I basically instantiate my new instance, right? So this second approach basically improves the overall performance of this design, right? But there is still one more flaw with this approach also. Let's talk about that now. Now, the thing that we have to understand here in the second approach is that this second approach is still not error free. Now, this again, if I run this code, you will see that it is still running absolutely fine. But this approach is not guaranteed to run on all the platforms correctly. Now, what I mean by this is, see, while when we are writing the code as a high level programmer or as a developer, we assume that this code would run absolutely correct on all hardwares and all the systems. But this is not the case. Now this is because the compiler has an option to optimize this code. Now you have to understand one thing here, that the CPU doesn't execute the source code. What it executes is a code which is generated by the compiler. Now the compiler always has an option to optimize these codes in such a way that they are more performant, and they are more performant with respect to CPU. They are also performant with respect to memory utilization, right? And apart from this, even the MMU, which is one of the memory management unit in the hardware itself, the CPU and the MMU are also responsible for a certain set of optimization. They do such optimizations for utilizing the memory bus in an efficient manner. For example, bunch up multiple small write operations into a single unit before sending it on the memory bus, right? So these set of optimizations is also done at the hardware level. Now, when it comes to compiler optimization, the compiler is always free to do a lot of optimization on your code, right? Because compiler is sole responsible for making your code to run as fast as possible, consuming as less resources as possible, right? So what could go wrong in this approach too? Let's try to understand this. Now the possibilities of going this code wrong can be many, right? Because we are not sure on what sort of hardware this code will be running, right? Because if you look at this code, right, there are many places where they are not atomic in nature. The operations are not atomic in nature. For example, initialization of this object. Okay, now one such optimization in compiler is that while you're doing this instantiation of this object might take, let's say, around 5 milliseconds to get created in the heap memory, right? Now when this object is being getting created in the heap memory, before it gets created, the address would be allocated. Now if you take this line number 39, let me just write it over here just to illustrate what is happening behind the scene. So say that this single instance is being initialized with the address of this new object, right? Now what would happen is, this is one part which is to create an object, right? This is the second part which is to take the address of that object, and this is the third part or the third operation which is to assign this address to this variable, right? And then a fourth operation might be to push this back to the memory, right? Because all these operations would be happening within the CPU registers, right? So there will always be a load and store operation which you will be having. So load is when you're pushing the data into the registers, and store is when you're pushing the data out of the registers to the memory, right? So if you look at this single instruction, it has almost around 4 micro operations, right? Now out of all these 4 micro operations, this first operation is the longest one. So let's say this operation, let's say if I'm instantiating a heavy object, this object initialization itself might take, let's say, around 5 milliseconds. Okay. Again, I'm making all these numbers up, but just to give you an idea, let's say this takes 5 milliseconds. Now the compiler always has an option to optimize for better CPU utilization and memory, right? So what it would do is, before the object gets fully initialized, it would have its address, right? And so what the compiler would do is, it would basically take this address and it would assign into this reference variable, right? So this reference variable would already have the address of this object. So wherever this object is being created in the heap memory, the address is already assigned to the single instance. Okay, mind that the object is still not assigned. I mean, the object is still not instantiated completely, right? It is still in the process of getting assigned, right? But the address is already put in the single instance variable. Now, so it might happen that the single instance variable is having some value. Now, so what would happen here is that though this object initialization is still going on, the single instance variable is no longer nil, right? It has got a value now. So now this return statement would return a value back. Okay. Now what would happen if there is a context switch and a new threads come into picture? That new thread, that T2, what it will do is, it will see this piece of code. It will see that, okay, it's not nil now. So let's say the single instance holds some address value, which is, for example, let's say 0x777. Okay, so it says that, okay, it's not nil, it has some value. So what it does is, it basically starts using that single instance variable. Okay, so let's say the thread 2 starts calling on that particular address. Now you have to understand that context switching is far more faster than this initialization of object variable, or this initialization of this object, right? Now if at this address some other object is present, or let's say some garbage value is present, the thread 2 might crash, right? So you cannot guarantee the correctness of thread 2 running, because the address at which this thread 2 is pointing to now is not yet fully initialized and replaced, right? So this is a major problem when it comes to this code, right? That due to compiler optimization and out of order execution, your code, which might look correct, which might also run correct on most of the times, but in some scenarios this code would yield unexpected output. And one major problem with this code is also that, since this inconsistency happens very rarely, you will not be able to reproduce this error, and then that becomes a really pain point. How do you reproduce this error and fix this, right? So this is one of the issues which is caused by this set of code, right? Now why is this all error happening? Now this error is happening all because of compiler optimization or out of order execution, right? So how do I fix this? Now different programming languages come with different approaches. So if you look at this line itself, right, if you see this, the major reason why there is an issue in this code is because this single looking instance instruction itself is made up of multiple micro operations, right? Now, so how do I fix this issue? Well, if we are using high level programming constructs, then we will not be able to solve this issue, right? So for this, the programming language itself has to give us some subatomic instructions which we can use of to get rid of this issue, right? Now, so every programming language has a inbuilt atomic instructions. For example, in Go, we have something called a sync package. Now that sync package itself brings in a lot of atomic operations to us, and we'll use the third approach to implement using those atomic operations. Similarly, in Java, we have volatile and synchronized keywords. Now these keywords ensures that such micro operations are happening in a certain order. Okay, so even if the compiler is trying to do things in out of order execution, these programming constructs like volatile, synchronized in Java, and in Go we have something called as sync.once. Such programming constructs help us to protect the code from getting out of order executed, right? So it basically enforces the compiler not to do so. Okay, so let's see the third approach now. All right, so if you see here, we have the third approach, which is called as the sync approach. So now this is very specific to Go, wherein I'm using a sync package. From the sync package, I'm using the once. So I'm basically creating a variable out of here. Okay, so this variable will basically initialize, or this variable will have a function called as do, which itself takes a anonymous function func, which has no inputs and which returns nothing. And within this function itself, I'm going to initialize my this thing, my sync object, my single object. Okay, now this function ensures that your object is always initialized once, and unlike the above approach where I'm basically checking the instance is nil or not and then I'm acquiring the locks and all, you don't have to acquire locks and all because all this is done within the do function itself. So if I click on and go to the definition of do, what you will see here is you'll see something called as atomic load. So if you see here, as I said, right, so you need to make sure that your operations are atomic in nature. So I'm using this atomic load and atomic store, right? And if you look at this, I'm calling a do slow function, which is basically acquiring the lock. And then it is again making a check and then it is doing a store. So this is how it is. So if you look at this code, it is very similar to the second approach itself, but here they're employing the atomic operations, which is the micro operations, which are always guaranteed to run atomically, right? And that's the reason why this approach is better compared to the second approach, right? And this approach is always guaranteed to run irrespective of whatever hardware you're running it. So it says that initialization of object is done, right? And it's not throwing anything else because I have not printed the else part here, but that's the whole idea here, that this is going to initialize everything as once, because even though if I'm calling 30 times my go routines, but this is only going to initialize it for the first time. After that, all of them are going to use this single instance variable itself. So I hope now you have understood why we are using singleton design pattern and how we can efficiently do it in Golang. So if you liked it, just hit the like button, and till then, bye bye.